Good afternoon, everyone. Today I'm going to discuss about the grid and cloud computing subject, Unit 3. So coming to the topic, in previous class we have discussed about the cloud deployment models, pros and cons of the computing, and implementation levels of virtualization. So these are the different topics we have discussed in the previous class. So I'm going to continue the topic, that is virtualization of CPU, memory and input-output devices. So in this virtualization of CPU, memory, and input-output devices, we having some types, that is hardware support for virtualization, CPU virtualization, memory virtualization, input-output virtualization, virtualization in multi-core processors, hardware support for virtualization, that is extended page table, and VTX, Intel's virtualization technology. So these are the different topics now I'm going to discuss in this virtualization of CPU, memory and input-output devices. Now coming to the first one, that is hardware support for virtualization. So before going to explain this, just I am giving the introduction about the virtualization of CPU. So to support the virtualization processors such as multiprocessors, to employ a special running mode and instructions known as hardware assisted virtualization. So in this way, VMM, virtualization machine made, and guest operating system run in different modes, and all sensitive instructions of the guest operating system and its applications are trapped in VMM. To save processor states, mode switching is completed by the hardware. So this is the introduction of the virtualization of CPU. So in this first one, that is hardware support for virtualization. So modern operating systems and processors permit multiple processors to run simultaneously. Okay, so in this we having some protection mechanism. So in a processor, so all the instructions from the different processors will access the hardware directly and causes the system crash. So these all processors have least two modes, user mode and supervisor mode. So it controls the access of critical instructions. So it controls the access of critical instructions and hardwares. Okay, instructions running in a supervisor mode in order to control supervisor mode are called the privileged instructions. Other instructions are unprivileged instructions. Other instructions are called unprivileged instructions. In the virtualized environmental, more difficult to make operating systems and applications run correctly because there are more layers in the machine stack. So in this we having the diagram. If you see that diagram, we can understand very easily. In this we having the hardware support by Intel. So next coming to example is the VMware workstation for the hardware support for virtualization. So next coming to CPU virtualization. So what is mean by CPU virtualization? So unprivileged instructions of virtualization machines runs directly on the host machines for higher efficiency. So other critical instructions should be handled carefully for correctness and stability. So the critical instructions are divided into three categories. So privileged instructions, control sensitivity instructions, and behavioral sensitivity instructions. So privileged instructions executes in a privileged mode and will be trapped if executed outside this mode. So that is called the privileged instruction. Control sensitivity means attempt to change the configurations of the used resource. Okay, so in these instructions, so whatever the configuration of resources is used, so that should be changes. So behavioral sensitive instructions. So in these instructions have different behaviors depending on the configuration of resources. So including the load and store operations over the virtualization memory. So in CPU architecture is virtualizable. It supports the ability to run the virtual machines, privileged and unprivileged instructions in the CPU user modes. So while virtual machine may run in supervisor mode, so the privileged instructions including control and behavioral sensitive instructions of virtual machine are executed, they are trapped in virtual machine layer. Okay, so in this RISC CPU architectures can be naturally virtualized because all the control and behavior sensitive instructions are privileged instructions. On the contrary, microprocessor CPU architectures are not primarily designed to support the virtualizations. So in this we are having the hardware assisted CPU virtualization. So this technique attempts to simplify the virtualization because full or virtual para virtualization is complicated. Intel and AMD add an additional mode called privileged mode level. So to microprocessor to privileged mode level to microprocessors. So therefore, in order to operating system can still run at ring 0 and hypervisor can run at ring 1. So all the privileged and sensitive instructions are trapped in the hypervisor automatically. Okay, so this technique removes the difficulty of implementing binary translation of full virtualization. It also lets the operating system to run in virtual machines without modification. Okay, so if in this virtualization we having the diagram. Okay, so this is the diagram what we have. Now we discussed what this can be done in this. Okay, so what they are saying here, I am having the applications. VM means virtual machines. So we are having the applications here, Win XP. Okay, Windows XP. This is the virtual machine root mode, and this is the CPU 0 and CPU 0, and this is the processor. Okay, so VT means what? Already we have discussed here. So VT is nothing but, so see, this is the VT. So what is Intel's virtualization technology? Okay, Intel's virtualization technology. VT means processor with Intel virtualization technology. Okay, so VTI. Okay, and we are having the virtual machine entry, virtual machine exit, and VMCS configuration, and VM virtual machine control structure, memory and input output virtualizations. So this is the main diagram of this okay, CPU. Okay, so in this memory, so what the main purpose of this memory? So here we are having the memory and input output virtualization. So what is the use of memory virtualization? So virtualization memory, memory virtualization is similar to virtual memory support provided by modern operating system in traditional environment. So the operating system maintains the page table for mapping the virtual memory. So virtual memory, it will be maps the virtual memory. Okay, so it will be maps the, so what will we do that in the traditional environment, the operating system will be maintains the page table for mapping the virtual memory to machine memory, memory to machine memory. Okay, and machine memory, which is one stage mapping. All the modern microprocessor CPU, all the modern microprocessor CPU include the memory management unit MMU, and memory management unit MMU, and the translation look aside buffer TLB translation look aside buffer to optimize virtual memory performance. So in this virtual execution environment, virtual memory virtualization involves sharing and physical system memory in RAM and dynamically allocating it to all the physical memory of the virtual machines. A two-stage mapping process should be maintained by the guest operating system, so and the virtual machine layer, and respectively. So all the virtual machine memory to physical memory, virtual memory to physical memory, and physical memory to virtual memory. So the virtual memory machine is responsible, VMM is responsible for mapping the guest physical memory and actual machine memory in the guest operating system. So whatever the things we have discussed in the previous, so this is the explanation of this diagram. So here what they are saying that in this we are having the applications. Okay, so what they are saying hardware. So in this we are having the applications. Okay, so here we are having the ring 0 and ring 3. Okay, and what they are saying that in this technology, in this virtualization, full or para virtualization is complicated. Intel and AMD additional mode called privilegied mode level. Some people can call it ring 1 and privilege microprocessor. Okay, microprocessor. So operating system can still run on the ring 0. Operating system can still run on the ring 0, and the hypervisor can run on the ring 1. Okay, ring 1. Okay, and the privileged and sensitive instructions trapped in the hypervisor automatically. Okay, so in this CPU CPU architecture is virtualizable. It supports the ability to run virtual machines. It still give the ability to run the virtualization machine, privileged and unprivileged instructions including the control and behavioral sensitive instructions and VM are executed. Okay, and they can be trapped the VMM. RISC CPU architecture can naturally virtualized because because the control and behavioral sensitive instructions and are privileged instructions on the microprocessor CPU architecture are not primarily designed to support the virtualization. So this is the working of this diagram. So in this we are having the virtualization virtual machines. These are VM means virtual machines. These are the applications, and this is the Windows XP. Here we are using the host operating system. Even still it running with the host operating system. In this we are having the VM entry. We are entering in the and exist. Okay, exist. And these are the control structure we are having. So they are the VMX root mode, and this is the virtual machine memory and input output virtualizations. Okay, so this is the parts of this diagram. So this is the hardware assisted CPU virtualization. Okay, so next coming to virtualization memory and input output devices. So okay, so what is mean by memory virtualization? So now only I discussed about this in this virtual memory. So I having this diagram. So this is the main diagram of the virtual memory. So I am going to explain about this diagram. In these virtual machines, here we are having the virtual memory, virtual VA memory, virtual PA memory, machine memory. Okay, VA, PA, MA. Okay, this is the VM1, virtual machine 1 and virtual machine 2. This is the processors. Okay, processor 1, processor 2, processor 1 and processor 2. Okay, so how it works? So having the here virtual machines. So operating system maintains the page table. Okay, now their page table for mapping all the virtual machines. So page table for every page we are providing the page. This is providing the numbers. The page table mapping all the virtual memory virtual memory to virtual memory to mapping the virtual memory to machine memory. Okay, mapping to virtual memory to machine memory, which is one core mapping. This is called the one core mapping. So all modern microprocessor CPUs include a memory management unit MMU and translation book look a side buffer, so TLB, to optimize the virtual memory performance. So in this virtual execution environment, virtual memory virtualization involves sharing the physical memory, sharing the system memory in a RAM and dynamically allocating the physical memory of all the virtual machines. Okay, so in the second stage mapping, processor should be maintained a guest operating system to operating system and the VMM. So virtual memory here, this is the virtual memory to physical memory and physical memory to machine memory. So the virtual machine virtual machine is responsible for mapping the guest physical memory to actual machine memory in a guest operating system. Okay, so this is the working. So such each page table in the guest operating system, each page table in the guest operating system has a separate page, separate page. Okay, and separate page in the VMM corresponding to it. VMM page table is called the shadow page table. Shadow page table. So this shadow page VMware uses the shadow page table to perform the virtual memory to machine memory address translation. Processors use the TLB. TLB means what? Translation look aside buffer hardware to map the virtual memory directly to machine memory, directly to the machine memory to avoid two levels of translations on every access. When the guest operating system changes the virtual memory to a physical memory, mapping the VMM update the shadow page tables to enable direct lookup. This is called the memory virtualization. So next coming to output virtualization. So it involves managing the routing of input output requests between the virtual devices and shared physical hardware. So there are three ways to implement the input output virtualizations. So that is called full device emulation. Full device emulation. So what we having what we said. So we having the three ways to implement the input output virtualization. One is full device emulation. So another is para virtualization, direct input output virtualization. So what is mean by full device emulation? So all the functions of this device, like device emulation. So this is the diagram. So what the use of this? So this is the full virtualization input output device emulation. So of all the functions of this device, like device emulation, device emulation, identification, interrupts, and DMA are replicated in the software, and it is located in the virtual machine. It is located in the virtual machine VMM and acts as a virtual device So what they are saying, this is the diagram. So what in the virtual device, what we are having? So device emulation, identification, interrupts, and DMA are replicated in this software. So and it is located in the VMM and acts as a virtual device. Okay. So in this virtual device, we are having the VMM. So in this VMM, we are having replicated some emulation, identification, interrupts, and DMA. Okay. So and input output acts as a request of the guest operating system. So input output, this is the input output. Okay. So input output stack access the request of the guest operating system. So this is the guest request of the guest operating and trap the VMM. So this is the VMM and which interacts with the input output devices. So okay, input output devices and next coming to this is called the full device emulation and in next coming to para virtualization. So in this method, it is a split driver model consisting of front-end driver and back-end driver, back-end driver. So front driver, back driver, which is the front driver and back driver. The front-end driver is running the domain U. The front driver running the domain U and the back-end driver running the domain 0. Okay, domain 0, and they interact with each other. So in this front driver, we have in this para virtualization, we having front driven and back driven. Front driven is running the domain U and back driven running the domain 0. So they interact with each other via block of separate spread memory, shared memory. The front driver manages the input output request of the guest operating system, and backend driver is responsible for managing the real input output devices and multiplexing of the input output data of different virtual machines. So para input output virtualization achieves better device performance than full device emulation. It comes with a higher CPU overhead. Okay. And coming to the direct input output virtualization. So what is mean by direct input output virtualizations? So in this virtualization, access the devices directly. So it can achieve close to native performance, okay, high performance without a high CPU cost. So the current direct input output virtualization implementation focus on networking. So another way of helping input output virtualization is via self virtualized input output virtualization. The key idea that harness to reach the rich resources of the multi-core processor. So all the tasks associated with virtualizing an input output devices are encapsulated in SV input output. SV means what? Self virtualization input output. Okay, self virtualization input output. So the self virtualization input output defines one virtual interface. So VIF for every kind of virtualized input output devices. Such virtualization network interfaces, virtual block devices, so we can say disk, so virtual camera devices and others. The guest operating system interact with the virtual interface via virtual interface device drivers. So each virtual interface consists of two message queues. So one is for outgoing message to the devices and other is for incoming messages for devices. So each virtual interface has unique ID for identifying it in a self virtualization input output. So this is called the direct input output virtualization. Next, called the virtualization in multi-core processor. So multi-core processors are climbed to higher performance by integrating multiple processor cores in a single chip. Multiple core virtualization has raised some new challenges to computer architect. So compiler constructors, system designers and application programmers. So the application program must be parallelized to use all the cores fully, and software must be explicit assign tasks to the cores, which is very complex problem. Concerning the first challenge, new assign task to the cores, which is very complex problems. Concerning the first challenge, new programming models, languages and libraries are needed to make parallel programming easier. So this is called the virtualization in multi-core processor. So in this we are having the virtual hierarchy. So a virtual hierarchy is a cache hierarchy that can adapt. A virtual hierarchy is a cache hierarchy that can adapt a fit the workload to mix or a mix of workloads. The hierarchy first level locates data blocks closest to the cores. So this is the diagram of the hierarchy. So in this virtual, this is the multiple virtual clusters assigned with various workloads. Okay, so this is the working of the diagram, and the virtual hierarchy is a cache memory. Virtual hierarchy is the cache hierarchy that can adapt fit the workload to mix the workloads, fit the workloads and mix the workloads. The hierarchy first level, this is the hierarchy first level, locates data blocks. In this we having the data blocks that close to the cores, needs to them faster access to establish a shared cache domain and establish a point to coherence for faster communication. The first level also provide isolation between independent workloads. A miss at the L1 catch can be invoked to L2 catch. Okay, so in this diagram, logical view of such a virtual cluster hierarchy in two ways. So two levels. Okay, so each virtual machine operates in isolated fashion at first level, within which minimizes both miss access time and performance interference with workloads or virtual machines. The second level maintains the globally shared memory, facilitates dynamically repartitioning resources without costly catch. Okay, costly catch. So this is called the virtual machine virtual hierarchy. And next, coming to virtual cluster and resource management. So what is mean by virtual clusters and resource management? So a physical cluster is a collection of physical servers. Physical cluster is a collection of physical clusters. Okay, in this cluster, collection of physical servers that are interconnected with each other. So I have the diagram. We can see this is the physical cluster. So what they are saying, so in this physical cluster is a collection of physical servers. Physical cluster is a collection of physical cluster. This is the physical cluster. In this we are having the physical what they are saying, physical cluster. Which is the physical cluster? This is the physical cluster, is the collection of servers interconnected with physical network, such as what they are saying. So one second. So this is the physical cluster is a collection of physical servers. Okay, physical cluster is a collection of physical servers. Okay, so physical servers means what? So physical cluster, this is the physical cluster and this is the servers. Okay, collection of servers is called physical cluster, one physical cluster. So okay, now, so what they are saying, a physical cluster is a collection of physical servers that are interconnected, physical servers that are all are interconnected. So in this is the physical cluster. In this physical cluster, having the group of or collection of physical servers. This is the server. These rectangular boxes are called the servers. Okay, so they are connected with each other by a physical network. This is the physical network. In the middle, we are seeing this physical network. So these are the physical machines. So we can say it is servers also. Okay, so physical machines, and they are connected with the physical network such as LAN. So this line is called the, so this cross lines is called the network. That network is called LAN, local area network. So whereas physical clusters, virtual clusters have virtual machines. So virtual cluster has virtual machines are interconnected logically by the virtual network. So what they are saying, this is the physical cluster. Okay, so this is the virtual cluster. So this physical cluster grouply is called physical servers. They are connected with the physical network called LAN, and a collection of physical cluster is called a physical server, and they are interconnected with the LAN network such as LAN. So here also the virtual cluster. So in this virtual cluster, we having the virtual machines. So they are interconnected logically by the virtual network across several physical networks. So we can study three critical design issues of the virtual cluster. Three critical design issues of the virtual cluster. Okay. Yeah. So in this issue, we dealt with her live migration, virtual machines, memory and file migrations, and dynamic deployment of virtual clusters. So in this, we will study three critical design issues of the virtual clusters. So live migration of virtual machines, memory and file migrations, dynamic deployment of virtual cluster. So virtual machines in a virtual cluster have following interesting properties. Virtual cluster nodes. So this is the virtual cluster. Okay. So the virtual cluster nodes can either physical or virtual machines. Physical or virtual machines. So what they are saying, in this virtual cluster, nodes can be either, in this virtual cluster, nodes can be either a physical or virtual machines, And the purpose of using virtual machine, the purpose of using these virtual machines is to consolidate multiple functionalities on the same server, and distributing same server. So virtual machines can be colonized, replicated in multiple servers for a purpose of promoting distributed parallelism, fault tolerance, and disastrous recovery. Okay, so the number of nodes of the virtual cluster can grow and shrink dynamically. The size of the virtual cluster, the size of the virtual cluster the size of the virtual cluster can grow and shrink dynamically. So virtual cluster will be changes according. It will be grows sometimes. Will be decreases. Okay, shrink means it will be decreases. So the failure of any physical nodes may be disable some virtual machines installed on the failing nodes. So whenever any node is failed, in that we can install the another one. Okay, failing nodes, but the failure of virtual machines will not pull down the host system. So the virtual cluster based on the application partitioning and customization. Most important thing is to determine how to store those images in the systems efficiently. So the common installations for most users are applications such as operating systems and user level programming libraries. The software package can be pre-installed as templates called template virtual machines. With these templates, users can build their own software stacks. New operating system instance can be copied from the template virtual machines. So in this we are having some types, that is fast deployment and effective effective scheduling. Okay, fast deployment and effective scheduling. So what is mean by fast deployment means? Fast deployment, before going to explain this, I having some here physical versus virtual clusters. So what is mean that virtual cluster can build with virtual machines installed at one or more physical clusters. The virtual machines in a virtual clusters are interconnected by the virtual network across several physical networks. The concept in this diagram we have seen now only. So the provisioning of virtual machines of the virtual cluster is done dynamically in following properties. The virtual cluster nodes is a physical and operating system. So now only we discussed about this so this is the points. And next coming to fast deployment and effective scheduling. So deployment means two things: to construct and distribute the software stacks, that is operating system and library applications, so to a physical mode inside clusters as fast as possible, and to quickly switch runtime environmental from one user's virtual cluster to another user virtual cluster. If one user finishes this using this system, the corresponding virtual clusters shut down or suspend quickly to save the resources to run other virtual machines for other users. So what they are saying, so whenever the deployment means two things: construct and distribute of software stacks of, that is operating system, libraries and applications. So whenever the physical node inside the cluster in physical node as fast as possible and quickly switch runtime environmental from one user virtual cluster to another user virtual cluster. If one user finishes using this system, the corresponding virtual clusters should be shut down and suspend quickly to save the resources to run another virtual machines for other users. So this is called the fast deployment and effective scheduling. Next, high performance virtual storage. So there are 4 steps to deploy a group of virtual machines onto a target cluster: preparing a disk images, configuring virtual machines, choosing the destination nodes, and executing the virtual machines deployment command on every host. Many system uses the templates. Okay, templates to simplify the disk image preparation processes. A template is a disk image that includes a pre-installed operating system with or without certain application software. Templates could implement the COW or copy and write format. A new COW backup file is very small and easy to create and transfer. So in this template, we must prepare the virtual machine constructions and usage of distributed to the physical host. Software packages can reduce the time of customization and switching of environment. Users should be identify their profiles that are stored in the data blocks. All the methods increases the performance in virtual storage. Example, Dropbox. We having some steps in deploying. Arrange and install a group of virtual machines onto a great cluster, So preparing the disk images, that is SSI, and configuring the virtual machines, choosing the destination nodes, executing the virtual machines deployment commands at every host. So these are the steps of the steps and target of the cluster. And next, live VM virtual machine migration steps. So there are 4 ways to manage a virtual cluster. First, we can use a guest-based manager by which the cluster manager resides on the guest system. In this case, multiple virtualization machines form a virtual cluster. We can build a cluster manager on the host system. The host-based manager surprises the guest operating system, guest system, and can restart the guest system on the other physical machines. The third way to manage a virtual cluster is to use an independent cluster manager on both the host and guest systems. Finally, we can use the integrated cluster on the guest and host system. This means the manager must be designed to distinguish between virtualized resources and physical resources. So a VM can be in one of the following. The virtual machines have following 4 stages: an active state, 4 stages, 4 ways. That is inactive. An inactive state is defined as virtualization platform under which VM is not enabled, and an active state refers to the virtual machine. So if you see the diagram, this is the diagram. So this is the 4 steps we are having. So in the first step, what we are doing, so an active state is defined by the virtualization platform under which virtualization is enabled. An active state refers VM that has been installed at the virtualization platform to perform a real task. Okay, so to perform a real task. In the step 3, we are passed to the state corresponds to the VM that has been instantiated but disabled to process a task or passed in a waiting state. So virtual machine enter the suspended state if its machine fail and virtual resources are stored back to the disk. So this is the another step. These are the steps involved in the live VM migration. So in this we are having the 4 ways. Guest-based manager. We can use a guest-based manager by which the cluster manager resides inside the guest operating system. For example, a Linux cluster can run different guest operating systems on the top of the Xen hypervisor. So we can bring the host-based manager, which itself is a cluster manager on the host system. For example, VMware high availability system that can restart a guest operating system after failure. A independent cluster manager which can be used on both the host and guest, making the infrastructure complex. Finally, we might also use the integrated cluster manager